Hey, today we are going to discuss a unsupervised technique called PCA. It stands for Principal Component Access. The goal of PCA is to identify the maximum variation in your data set. It's a dimensionality reduction technique. Means if your model is having tens of thousands of parameters or features, you can use PCA to select subset of features which carry most of the information. By most of the information means again taking the same example, suppose you have 100 features, you can ask PC to get the number of features which covers 99% of the variation, meaning it can cover, it may have 4 features, it may have 5 features, or it may end up having 90 features. But it depends on what amount of data is covering your variation. So what PC does is, it's instead of looking into a subset of original features, it try to find out a separate dimension in which it tries to project the original data and end up having a different dimension. So what you're having right now is things which work in the PCA. So there are some really good articles which have been taken as a references. I've explained or included them here. So you can just follow the links in the shared document and you can actually go to these articles. They are really good. So the references have been taken from this. So let's try to summarize how this feature actually work. So before summarization of the PCA, there are two topics which we need to understand. These topics are what is the variance and what is the covariance. So before diving into PCA, this is essential. So what does variance mean? So variance is nothing, just calculate the spread of your data. So if your data is largely spread, the variance will be much larger there. If your data is aggregated to a particular axis, the variation will be less. So this is a formula which you can use to calculate the variance, and this is a formula which you can use to calculate the covariance. So the formula for variance is xi minus x bar whole square divided by n square root. Now what is a covariance? What covariance does is it try to identify how two variables are acting together. Means it can only take a value between -1 and 1. So if a variable is inversely proportional to a second variable, meaning increasing the value of one variable will decrease the value of other variable, means they have a negative covariance. Means value is closer to -1. And if both the variables increase simultaneously, then they have a positive covariance. And if there is slightly no change, it means they don't have any covariance between them. The covariance value will be 0. So these are kind of a graph which is showing the covariance in that direction. Like here, increasing the value of one variable, decrease the value of other variables, so the negative covariance. And this is perfect case like x is here and y is here. Increasing the value of x, increase the value of y. They have a large positive covariance, but here we don't have any patterns. That's why they have a near zero covariance. So these two topics are kind of essential when dealing with PCA. Now let's dive into PCA. So as I said, how does PCA work is it tries to identify a different dimensional plane which captures maximum information for data. So what we are trying to do is firstly, we have the original data, we are going to standardize it. Because if you're not going to standardize the data, we are going to observe patterns which are different. So this is a standard technique. You can either normalize the data or you can use a min-max scaler to just put them in a range of min-max. Now, based on the above concepts, we will try to calculate a covariance matrix. So what's happening here is, suppose if we have 5 features, so it will calculate a 5 by 5 covariance matrix. It means we will try to calculate the covariance of each feature with the other feature. Now, uh, you will notice that diagonal elements have been written as V instead of C. What means is, here we are calculating a variance, not a covariance, because we cannot calculate the covariance of A with itself. It will always be 1. So here we'll end up having VA. So similarly, like here, again, they have replaced the covariance with the variance. So diagonal with the variance and the other element is the covariance. Now, the other topic that we are going to do is we are going to calculate the eigenvectors and corresponding eigenvalues based on this covariance matrix. So this is the formula for that. This is a well-defined formula. In order to calculate the eigenvector, eigenvalue, what we are going to do is we are going to put this covariance matrix here, and then we are going to calculate what the value of eigenvector could be or what the value of eigenvalue would be. So what does eigenvector and eigenvalue mean? So eigenvector is nothing. It just try to capture the direction which has the maximum variance. By maximum variance means which try to capture the maximum information, and the eigenvalue checks the magnitude of the variance in that direction. So if we have n-dimensional plane, we can have at most n eigenvector. The reason why we can have n eigenvectors is because each eigenvector is perpendicular to the other eigenvector. So so suppose if we are working on a three-dimensional plane, we can only make three vector perpendicular to each other. That's why we can have only n at most eigenvector. So our job is to calculate the first eigenvector, and the first eigenvector which contains the maximum variance, and the other eigenvector will always be perpendicular to it, and the third one is perpendicular. Will be going to perpendicular to both the eigenvectors, and similarly all the others. So here is a solution which try to calculate the covariance matrix. Okay, it's of a different equation. Don't worry about the original equation. But this is suppose a covariance matrix. This is a variance, and this is a covariance. So this is a symmetric matrix means V covariance of A comma B is going to be covariance of B comma A. They are going to be the same. So our idea is to find a new metric system in which we will try to zero out this covariance, and we will try to capture all the variance among the diagonal elements only. Means the diagonal elements will retain value, whereas the other non-diagonal elements will reduce to zero. So our aim is to get there. Now, as I said, we'll calculate the eigenvector and eigenvalue based on this formula. So once we have our n eigenvector, our next job is to sort the eigenvector based on the eigenvalues. Now, by sorting means the vector with the maximum eigenvalue will be first, and then in a decreasing order. So suppose our goal is to reduce the dimension of the original data from 100 to suppose say 4. So we'll pick the topmost 4 eigenvectors, and the eigenvalue will tell us how much variation among the whole data set that is actually encounter. And we can also do it in different ways. Suppose if you said we want to capture 99% of the variance, so we'll see how much vectors are required to calculate the 99% variance. We'll just simply sum up all the 100 variance and see where the 99 threshold is meeting. That way we can reduce the number of dimension using that formula also. Now there's one point I want to make. When we project a dimension, the original dimension into another dimension, we will lose some information because there's no way we can be perfect. In very rare scenario, we'll lose no information, but in most of the scenario, we will lose some of the information. So another way of explaining this is suppose if we have this, so there's some information that we will miss. So I was giving an example of a two-dimensional matrix. Suppose if we try to project this data into another two-dimensional plane, there's no way we can project maintaining all the accuracy. So we will definitely lose some of the information. Projecting this is simple because we can just put a new dimension such that the first dimension is along this line, and the second dimension is perpendicular to this line. This way we can maintain most information, similarly in this case. But in this case, we are going to miss some of the information. Now, coming on this part, so after choosing how many eigenvectors we want to retain, we need to transform the original data into the data of other dimension, the ones we have projected using eigenvectors. So just multiply simply the eigenvector with the original data. Now, in the new coordinate system, which we'll get, will have the new covariance matrix, which will look like this. Means it is a diagonalized matrix only. All the other non-diagonal elements are zero. So that's our original intention. Now we have the working PCA in there. Completion. So now we can just plot the new data, and the way we are going to plot it, suppose if we have this two-dimensional data and we have projected the new dimensional data into two-dimensional plane, what we are going to do is we are also going to populate the original data points that it is supposed to have. So as you can see in the original data plane, the original plane will look like this, and this is a completely different plane. So this way, how the PCA work. Now to verify whether your PCA has captured all the variation, what you can do is just an indirect comparison. So you will have the first model, you must be getting some accuracy like 80%. So when you apply a model on the new data set with reduced number of points, you should be getting accuracy nearly same as the original one, like 80% or 70%. It should not be drastically low. So if it is drastically low, it means something has gone wrong with PCA. You need to revisit it. Otherwise, it's okay. Means you have done the transformation PCA correctly. So yeah, that's related to PCA.